Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We're looking at a virtual work for this particular problem. We want to determine the equilibrium position, okay, and to solve the equilibrium position as well as the stability for that position. To determine this, we will determine uh, the potential function, differentiate the potential function, and set it to zero to determine the equilibrium position, right, at theta, as well as for the stability, take the second derivative with respect to theta as well, okay, and of the function, and set and solve the resulting uh, equation, plugging in our theta that we had earlier gotten, and determine the stability, right? So we have this, and for this one we have something here. We have a block down here. Okay, okay. We have a block there, and then we have this the weight. Let's call it W2, right? And of course, the mass is going to have 7 kg. So we are going to have the height, the vertical height, uh, this. So let's call the vertical height. Let's call it Y. Subscript B for the block. Okay, from that point, and we are going to also consider uh, the the weight of the the weight of the this member AB, okay, as well as BC. Okay, okay. Let's call it the weight W subject one. All right, we are going to have at this point the the height. So you can see that the datum is at AC. Okay, so we can call this Y subscript Y subscript M, and of course Y subscript M, and of course this goes also for this other weights. Okay, we are going to have, all right, which is also work also called W subscript one because it's equal to this other these two AB, length AB. Remember, AB and BC they are equal in length as well as in mass. So we have that. So YM is also for this member is also equal to that for BC as well. So that if we consider the bars, okay, AB and BC, we are going to have Y1 substitute one rather to be equal to half. Okay, for one bar, Y1 is going to be this times 0.5 sine theta. Of course, AB is 0.5 meters. Okay, from converting it from 500 millimeter to meters, that's what they're going to have for one bar. They're going to have that. So Y substitute one is equal to 0.25 sine theta, sine theta. So we have that for that. All right. And of course, we know that the potential uh, gravitational potential energy, we can call this one VG, okay, VGM, okay, so it's going to give us is equal to W. Okay, sorry, I recall this. So this is y source with m. Remember from the diagram there. So we are going to have this one to be y times y source with m. Okay, that's for one of the member. Okay, AB or BC, one of them. So, but we'll consider the two into when we are plugging in values into the full equation. All right. For the block, we are going to have x. Okay, this distance from here to here. This is x. Okay. All right. So for x, x is going to give us equal to um, 0.5, okay, cos theta, okay, cos theta plus 0.5 cos theta, right? So that's what we are going to have for this one. And of course, this distance is given to us between A and let's call this E, between here, point A and E. Let's call this point E. The distance given to us as 0. Sorry, yes, between that point is given to us as 0.5 meters, which is 500 millimeter, which we have converted to to meters. So we have that so that our y sub root b is equal to 1 minus x. Remember that the length of the string from C down to let's call this point D is 1 meters. Okay, one meters. Okay, all right. It's given to us as one. It's given to us. Okay. Now we can also go ahead and just get our y sub with b, so that y sub with b is will be equal to 1 minus in fact when we plug in everything there that we just have now, let's just plug it in. We are going to arrive at 1.5, okay, 1.5 minus cos theta. Okay, so that's what we are going to have for that. So we can just consider uh, the potential function is going to be equal to v subscript g m, okay, plus, and of course you know that we have for v subscript g m they are we have two of them there. Okay, so this v, okay, v subscript g m 1, okay, so there are two anyway, there are two of them there. Okay, v subscript g m v subscript g m is for those members a b and b c. There are two. Okay, then plus the block plus V subscript GB. Okay, so these are the gravitational potentials. Okay, energy. So that if we plug in values, we are going to have these to be, in fact, the potential. We're going to have a positive potential energy for these first for the link for the members AB and BC because they are above they are the their center of gravity, okay, is above the datum AC. Okay, all right. So we're going to have this to be. Okay, let's see, put it this way, plus W, okay, right source with M. And for this one, it's going to give us negative because it's below the datum. So we're going to have this one to be W. Okay, let's just differentiate. And this is W1. Let's call this W1. Then let's call this W2. Okay, W2 Y source with B. All right, so that Y source with B. So let's see how we label this one here. Yes, you are correct. So we put it here. This is W source with 1. Okay, so we can now come here and okay. So if we do that, we plug in values into this, we are going to arrive at V to be equal to 14.7 sine theta, 74 sine theta, 10 theta plus 68, 68.67 cos theta, okay, minus 103.01 minus 103. Now the value of W1 is given and the value of W2 is given. So W1 is 3 kg, so multiply by 9.81, as well as W2 7 kg. So multiply by 9, and you have this value, multiply them by the okay, the heights. So that if we do that, if we take for equilibrium, we can take the second the derivative. Okay, the first we can differentiate potential function now with respect to theta, so that we will have and set it to 0. We are going to arrive at 14.74 cos theta cos theta. Okay, minus 68.6, 68.67 sine theta. Right, and set it to 0. So if you solve this, you are going to arrive at theta to be equal to, of course, you are going to have tan and take the arctan. You have tan theta to be equal to the value, and take the arctan of that value, and you are going to arrive at theta to be equal to 12.11 degrees. Okay, then for the stability, we can take the second derivative, okay, of the potential function with respect to theta. If you do that, we are going to have the squared v, the theta squared is equal to, when we do that, we are going to have it to be minus 14.74, right, sine theta, okay, minus 68.67 cos theta, right? So if we plug in values into this, we are going to arrive at this to be equal to minus 70.23. Just plug in the value of theta that we have gotten 12.11, okay, degrees. So we are going to arrive at this, which of course you can see that this is less than zero. So this equilibrium is an unstable equilibrium. Okay. All right. So these are the answers.